So, everything from your Wi-Fi router to the 5G on your phone, it all runs on these signals that we can't see or hear or touch, right? So the big question is, how do engineers actually build and perfect all this stuff that powers our entire connected world? Well, they do it with a really special toolkit, one that, you guessed it, makes the invisible visible.
And really, that is the million-dollar question, isn't it? How do you measure something you can't see? I mean, these wireless signals are literally all around us right now. It's like the super complex, high-speed dance of electromagnetic waves. So if you're trying to design an antenna or build the next smartphone or just figure out why a network is slow, you've got to have a way to see what's actually going on.
So that brings us right to the heart of the matter, the big invisible challenge. This is really the core of what radio frequency, or RF, engineering is all about. See, these signals, they aren't just invisible, they have a bunch of other quirks that make them super tricky to handle unless you have the right gear. Okay, so let's break down this problem. First, yeah, they're invisible. We've covered that. But second, they operate at these mind-bogglingly high frequencies. We're talking billions, with a B, of cycles per second. And on top of all that, they're really delicate. They get messed up so easily by noise from other electronics or get totally drowned out by interference from other signals flying around. That's why we need these special instruments to analyze, measure, and basically debug these incredibly fragile and fast-moving signals.
All right, so how do we actually see these things? Well, engineers have two main ways to look at a signal, and they give you two totally different points of view. It's kind of like having two pairs of magic glasses. One pair lets you see how a signal is behaving from moment to moment, over time. And the other pair shows you what frequencies it's actually made of.
First up, we've got the oscilloscope, and I bet you've seen this one before, probably in a movie or a TV show. It's that classic screen with the wavy green line, right? This tool gives you a peek into what we call the time domain. Basically, it answers the question, what does my signal's voltage look like? Right now, and now, and now. It's absolutely perfect for looking at the exact shape of a waveform or trying to fix timing issues in a circuit.
Then, on the flip side, you have the spectrum analyzer. And let me tell you, for a wireless engineer, this thing is probably the most important tool in the entire box. Instead of looking at time, it looks at the frequency domain. It shows you exactly which frequencies are inside your signal and how much power each one has. This is absolutely critical for things like checking if your signal is on the right channel, measuring how wide it is, or, and this is a big one, hunting down nasty interference.
This really nails the difference. Think of it like this. An oscilloscope is like a super high-speed camera. It just snaps the picture of the signal and freezes its shape in one instant. A spectrum analyzer, though, that's more like a prism for radio waves. It takes the whole signal and splits it apart into all its different colors, or, in our case, all its different frequencies. So you've got two different tools giving you two totally essential views of the exact same invisible thing.
Okay, so now that we've got our basic eyes to see these signals, let's put it all together. Let's see how these tools, plus a few more, actually fit into a real-world design workflow. We're going to follow a signal on its journey all the way from creation to analysis.
You can pretty much think of a typical workflow like a simple three-act play. Act 1, you have to create the perfect signal. This is your hero. Act 2, you send that hero on a journey, right through whatever device you're testing. And Act 3, you analyze what comes out the other side to see how the journey changed it. Simple, right?
So for Act 1, creating our hero signal, we need a signal generator. This is ground zero. Its whole job is to pump out these super precise, super clean RF signals that you can completely control. You get to tell it exactly what frequency to be, how much power to have, and even what kind of data to slap onto it. This is how you test if a receiver can actually, hear the signal it's supposed to be listening for.
All right, Act 2. This is where we figure out what the journey is like. And for that, we need a beast of a machine called a vector network analyzer, or VNA for short. This is a really powerful tool. What it does is it sends a known signal into something, say an antenna, or a filter, or even just a cable, and it measures with incredible detail every little thing that happens to that signal as it goes through.
So what the VNA is actually measuring are these things called S parameters. Now, don't get hung up on the name. It's actually pretty simple. Think of it as the VNA asking two main questions. The first one, S11, basically asks, hey, when my signal hit the front door of this thing, how much of it just bounced right back at me? It's just like seeing your reflection in a window. The second question, S21, asks, okay, of the signal that went in, how much actually made it out the other side? That tells you how much signal got lost along the way, kind of like how a tinted window dims the sunlight. Answering those two questions is Well, it's everything when you're designing good hardware.
And that brings us to Act 3, analyzing the output. Now, for today's super complex digital signals, we're talking Wi-Fi, 5G, all that good stuff, a regular spectrum analyzer sometimes just doesn't cut it. You need something smarter. You need a vector signal analyzer, or VSA. This is a seriously sophisticated tool. It can actually decode those complex signals and measure their quality with insane precision. It tells an engineer exactly how messed up their signal got along its journey.
Now, all this specialized hardware we've been talking about is incredible, for sure. But it has two big problems. It's crazy expensive, and it's not very flexible. And that's where a huge revolution in the RF world comes in: software-defined radio.
So what is software-defined radio, or SDR? Well, the core idea is pretty brilliant. You replace as much of that dedicated chunky hardware as you can with clever software. What you end up with is a radio that's insanely flexible. You can literally program it to do what you want. You can get devices like a USRP or even a super cheap little RTL SDR dongle, and you can tell it, hey, today you're a signal generator. Tomorrow you're a spectrum analyzer. It's this chameleon-like ability that makes SDRs an absolute must-have for cutting-edge research, especially in things like 5G, and it's why you see them in basically every university lab.
Okay, so we've hit the big ones, but an RF engineer's toolkit has a few more specialized gadgets for very specific jobs. Let's round out the list. Let's touch on two more key pieces of gear. First, the RF power meter. Its job is dead simple, but totally crucial. It just measures signal power with really high accuracy. You need this to make sure a transmitter isn't breaking the law with its power output or to verify it's performing like it should. Then you have these specialized antenna setups. These things are designed to map out exactly how an antenna radiates energy in 3D space, showing you precisely where its signal is strongest.
And look, this isn't just stuff you find in a university lab. This equipment is the absolute lifeblood of the entire wireless industry. You've got giant companies like Keysight Technologies and Rhoda Schwartz, whose entire business is building this ridiculously precise and complicated gear. They're the ones who make the tools that power innovation at pretty much every big tech company you can name.
But we gotta be real here. Working in this field isn't all fun and games. There are some serious challenges. For one, this equipment is, well, it's staggeringly expensive. We're talking luxury car prices for a single high-end analyzer. And you can't just pick it up and use it. You need a really solid grasp of engineering fundamentals. Plus, just setting up a measurement to get an accurate result can be a really complex art form all on its own.
So, let's wrap this all up. When it comes down to it, RF test equipment is our window. It's how we peek into that invisible world of wireless. Whether it's the oscilloscope showing us the signal's shape over time, the spectrum analyzer breaking it down by frequency, or the network analyzer telling us how our hardware behaves, every single tool has its own special job. And together, they're what make it possible to build a technology that keeps us all connected.
And that leaves us with one final big question to think about. Our world is only getting more and more wireless, right? We're pushing towards 6G, the Internet of Things. Everything is going to have a signal. And those signals are going to get faster, more crowded, and way harder to measure. So the real question for the future is, what will the next generation of these tools even look like? What new clever ways are we going to have to invent to keep making the invisible visible?